To value an ecosystem service, we first have to isolate exactly what part of the environment we are evaluating. We begin with environmental goods that are physically harvested and traded in markets. We are dealing with tangible commodities: timber, medicinal plants, and commercial fish harvests. We are not yet measuring abstract services like clean air. That assumption is a complete economic fallacy. Environmental economics requires a far more rigorous metric. We have to determine the total economic surplus. To measure an ecosystem's actual worth, analysts must look past the transaction at the cash register and map the underlying economic behaviors of both the buyers and the suppliers. This theoretical graph models market behavior. The downward curve represents demand. Consumers have an absolute maximum price they are willing to pay for a resource. The difference between that theoretical maximum and the actual market price they pay is the consumer surplus. Suppliers operate on the upward curve. Producer surplus is the total revenue earned from selling the good, minus the escalating, compounding costs required to physically bring it to market. Those escalating costs accumulate quickly in the real world. For a fishing fleet, catching additional units means pushing into deeper water, burning more fuel, executing heavier boat repairs, and paying crew members overtime. Adding the consumer surplus and the producer surplus together yields the total economic surplus. This combined geometric area represents the absolute maximum benefit humanity derives from the existence of the resource. Any environmental policy or ecological change must be judged by exactly how much it expands or shrinks this specific area. We can now introduce a disruptive ecological variable into this framework. A severe toxic pollutant leaks into the water, destroying local breeding habitats and decimating the regional fish population. The immediate mechanical effect hits the suppliers. With the population in steep decline, fishermen are forced to spend exponentially more time, fuel, and physical labor searching the ocean just to secure the exact same volume of catch. Returning to our graph, these increased search costs forcefully shift the entire supply curve to the left. The secondary effect hits the market floor. Fewer fish available forces consumers into bidding wars, aggressively driving up the retail price. The precise economic damage caused by the pollution is calculated by subtracting the new restricted surplus from the original healthy surplus. This mathematical difference, the lost geometry on the graph, is the true financial cost of the environmental change. Environmental degradation is a direct, measurable destruction of human economic value. The logic of the surplus model is airtight, but how do economists actually figure out the precise shape of a demand curve in the real world? The theoretical ideal would require multiple parallel universes, allowing us to test identical consumer populations with varying prices to perfectly track how much volume is traded at each tier. In reality, analysts start with historical price and quantity data. This plots out as a chaotic scatterplot because price is never the only factor dictating market behavior. That data is corrupted by external variables. Changing prices of substitutes, shifting incomes, and migrating populations warp the numbers. To clean this mess, economists rely on regression analysis. This statistical engine filters out the noise of those external variables. By isolating just the pure relationship between price and quantity, regression reverse engineers the mathematical equation required to draw a proper demand curve. Supply curves demand an equally rigorous process, requiring analysts to meticulously audit the historical catch costs of actual fishing fleets. Here is the fatal flaw for practitioners. While regression provides a mathematical best guess, it demands a massive, pristine dataset. Field analysts almost never possess that luxury. Policy work happens in the trenches. Environmental analysts are routinely constrained by tight legislative deadlines, limited operating budgets, and severely scarce historical data. When complex regression is impossible, analysts turn to a controversial but highly common shortcut: the net benefit equation. The first half of the shortcut is crude but effective. Analysts simply multiply the total volume of fish produced by the current market price to estimate the gross value. For the second half, they audit the fleet to calculate the heavy mechanical and labor costs and subtract those real-world expenses from the gross value. This equation contains a glaring theoretical flaw. By substituting raw total revenue for a meticulously calculated demand curve, analysts completely erase consumer surplus from the math. Economists willingly accept this massive compromise for two very specific reasons. First, policymakers and the voting public easily understand the concept of revenue minus costs. Abstract surplus curves cause political friction and confusion. Second, an imperfect, slightly undervalued metric is infinitely better than having no metric at all. In conservation economics, a functional number delivered on time holds far more utility than a perfect theoretical model delivered after the ecosystem has already collapsed. This exact shortcut was deployed to evaluate the marine ecosystems of the Agulhas bioregion in South Africa. 3 existing marine protected areas along this rugged coastline were actively threatened by commercial exploitation and industrial pollution. The proposed solution was to radically expand the protected zones. The immediate conflict was that doing so legally banned local fishermen from accessing those waters. Closing that section of the ocean creates a severe opportunity cost. It removes fishable area and directly strikes the fleet's bottom line. The biological defense of the policy is that a closed, protected area acts as a safe spawning ground. Given time, it will overflow and seed heavily harvestable populations in the surrounding legal waters. Local resistance was fierce. The money stopped immediately for the fleets, while the promised biological benefits felt entirely theoretical and distant. The government faced a rigid policy tension. They had to quantitatively prove that a guaranteed short-term financial loss was worth a theoretical long-term biological gain. Using the market-based shortcut, the research team calculated the volume of fish migrating out, multiplied it by the market price, and subtracted the opportunity costs of the newly closed area. They executed this despite facing extreme data limitations. Out of a dozen primary catch species in the region, the researchers only had reliable migration data for 2. They were forced to extrapolate blindly to account for the rest of the ecosystem. This chart maps cumulative costs and benefits over 20 years. The flat line is the baseline scenario. The secondary line tracks the expanded protected area. In the initial phase, this line takes a sharp dip, representing immediate net losses for fishermen due to lost territory. But the inflection point arrives. As the internal fish populations fully recover and migrate out of the safe zone, the economic yields eventually overtake the initial losses. Using a standard 6% discount rate and explicitly overestimating the costs while aggressively underestimating the benefits, the expanded protection zone remained mathematically profitable. Even when forced to rely on pragmatic shortcuts and fragmented ecological data, market-based valuation provides a translation layer. It allows analysts to frame conservation not just as an environmental goal, but as a legible asset management strategy.